Okay, so today we're going deep, really deep into a topic that I think kind of sits right on the edge of, like pure logic and how we understand reality itself.
Ooh, sounds intense.
It is. We're talking about nominalism,
Nominalism.
specifically nominalism in the philosophy of mathematics.
All right, I'm intrigued. Break it down for me and for our listeners, of course.
So basically, it's all about questioning whether those mathematical objects, the numbers, sets, all that stuff we use all the time, whether they actually exist as like real independent things.
You mean like is the number 3 floating around out there somewhere?
Exactly. Or is it just like a symbol, a tool, a kind of useful fiction we've created to help us make sense of the world?
Okay, I see. So like is math discovering truths about some separate realm of numbers, or is it more like inventing a really powerful language to describe things?
You got it. And for this deep dive, we're taking a close look at a super in-depth article from the Stanford Encyclopedia of Philosophy. It's called, well, straightforwardly enough, Nominalism in the Philosophy of Mathematics.
Nice. Always a good source.
It goes into all the different ways philosophers have tried to, grapple with making sense of math without having to believe in a whole universe full of abstract objects.
The whole universe, huh? Platonists probably wouldn't like that characterization.
Haha, probably not. But that's the core tension here, right?
Mhm.
I mean, math is arguably the most successful way we have to describe and explain how the world works. But the big question is, do we have to believe that all those numbers and sets and things actually exist out there somewhere to explain that success?
It's a heady question for sure, and one that can lead you down some pretty dense philosophical rabbit holes.
Oh yeah, the philosophy of math can get super complex fast. I mean, you start talking about different levels of infinity and whoa, things get weird.
For sure, and the jargon can be a bit much too.
Totally. So what we're trying to do here is to really boil down the most crucial arguments and challenges that surround nominalism, present them in a way that makes sense, with clarity, structure, all that good stuff.
Yeah, we don't want to lose anyone in a sea of technical terms.
Exactly. And we're approaching this as if we're explaining it to another philosopher, someone who really gets the depth of these kinds of questions. So that's you, our listener, the philosopher in our midst.
I like it. Treating our listeners as fellow inquirers.
Because it's not just about definitions, right? We want to get into why these ideas matter, what the implications are, what's at stake in this whole debate.
Absolutely.
Mhm.
It's about grappling with the foundational assumptions we make about math and how those assumptions shape our understanding of reality.
So, to give you a roadmap of where we're headed, we'll start by laying out the fundamental clash between nominalism and its main rival, which is Platonism.
Right, the classic battle of the math philosophies.
Then we'll go through what the source identifies as the 5 key problems that any philosophy of math needs to deal with.
This is like a challenge.
Oh, it is. And we'll look at how nominalism tries to address each of these problems.
Well-
And finally, we'll explore some of the most prominent, like present day versions of nominalism to give you a sense of like the current state of this whole philosophical conversation.
Sounds like a plan.
It's all about getting to the bottom of like what math really is and how it connects to, well, everything else. So first things first, let's talk about this clash between nominalism and Platonism.
All right, let's do it.
Our source makes it super clear that Platonism, when we're talking about math, is the view that mathematical objects, things like, the number 7, pi, the set of all even numbers,
The usual suspects.
right, that all these things actually exist. And crucially, they exist in a way that's abstract, meaning they're not physical things. Like you can't reach out and touch the number 3. It doesn't have a location in space or time, and it doesn't, cause anything to happen in the physical world.
So it's not like saying the Eiffel Tower exists in Paris. It exists in some other non-physical way.
Exactly. It's kind of like, well, the Platonist would say it's just as real as the Eiffel Tower, but in a different way. It's out there in some realm of abstract objects. And for the Platonist, mathematical truths are true because they describe this like separate mathematical world correctly.
So like 2 plus 2 equals 4 is true not because of anything in the physical world, but because of some fact about this abstract realm of numbers.
Right. It's a realist view about math through and through. Now let's flip the script and look at nominalism. The fundamental idea here is that mathematical objects either don't exist at all or
we don't need them.
yeah, or we don't need to assume they exist to do math, to understand it, to use it effectively. The nominalist is basically saying, hey, do we really need this whole other world of abstract stuff to explain why math works?
Right, like maybe we're making things more complicated than they need to be.
And the skepticism, as our source points out, puts a big burden on the nominalists.
In what sense?
Well, they can't just say, numbers don't exist, case closed.
True.
They have to come up with an alternative explanation, right?
Right.
Right.
How do we do math? How is it so successful in science and engineering and all these areas if it's not actually describing a real realm of mathematical objects?
So the nominalist has to do just as good a job as the Platonist in explaining why math works, but without appealing to those mathematical objects.
Exactly. They need what the source calls a meager ontology, a much slimmed-down view of what exists in the world.
It's like a philosophical Marie Kondo situation.
Uh-huh. Does this number spark joy?
Exactly.
So to pull this off, nominalists have to get into some really deep philosophical territory. They have to talk about metaphysics, like what is the nature of existence, and do numbers and sets qualify as things that exist?
It's not just about counting anymore.
Nope. It's about the nature of being itself. And then there's epistemology, the study of knowledge. Like, how can we possibly know anything about mathematical objects if they're not part of the physical world, if we can't interact with them?
Right, if they're not causing any effects that we can observe. And then, really crucially, there's the philosophy of science. Like, if math is all about these non-physical, non-causal things, how in the world is it so useful in describing and predicting things in the physical world?
Yeah, that's the real puzzle. I mean, if math doesn't connect to the world in any way, why should it be so good at describing it?
Totally. Okay, so before we get into the problems of math, let's just quickly acknowledge that neither Platonism nor nominalism is like one single thing.
What do you mean?
I mean, there are different flavors of each. So
Right.
like with Platonism, you have standard Platonism where those math objects are, like the standard bearers.
Yep.
But you also have structuralism where it's more about the relationships between mathematical objects that are important. And then there's even full-blooded Platonism, which is, well, let's just say they're really committed to those math objects.
Full-blooded, huh? Committed is an understatement.
And nominalism is just as varied. You have fictionalism, where math is seen as a kind of useful story we tell. There's modal structuralism, which uses the idea of possible worlds to make sense of math. There's constructivism, where math is seen as something we actively build or create, and others.
A lot of different tools in the nominalist toolbox.
And our source is going to be focusing on some of the most influential contemporary versions of nominalism to give us a taste of the current landscape.
Perfect.
Oh, and one more thing before we move on. The source mentions that the modern debate about this stuff really got going in the 20th century, thanks in part to folks like Quine and Goodman.
Familiar names.
They were trying to develop what they called constructive nominalism, but ran into some issues, especially when they tried to talk about, classes or sets without invoking those abstract objects.
That seems to be a recurring theme.
It is.
Mm-hmm.
But their work laid the groundwork for later developments, and a really central question that's driven a lot of recent nominalist thinking is, how do we respond to the argument that math is absolutely essential to our best scientific theories?
Yeah, that's the crux of it. If math is so fundamental to science, and science is describing the real world, then what does that say about the status of math itself?
Okay. Now, just to make sure we're all on the same page, mathematical nominalism, the kind we're talking about here, it's different from the old debate about nominalism when it comes to universals, like the whole question of whether properties like redness really exist or if it's just a name we give to a bunch of red things.
Ah, right. So we're not getting sidetracked by questions about whether there's some abstract redness floating around.
Nope, we're sticking with the math.
Sticking with the math. I like it.
So, are you ready to tackle those 5 key problems in the philosophy of math?
Hit me with them. Let's see how nominalism measures up.
Okay, the first one is the epistemological problem. And it's basically this. How in the world do we know anything about mathematical objects if they don't, causally interact with us?
It's a good question. It's like trying to study something in a completely different dimension.
Yeah, if these numbers and sets are floating around in some abstract realm, completely separate from our senses and our experiences, how can we ever learn anything about them?
Like if they don't cause any effects in our world, how do we even know they're there?
Now, this is often seen as a big strike against Platonism. Platonists have tried to explain it by talking about, mathematical intuition.
Intuition.
You know, like we just have this innate grasp of mathematical truths.
Okay.
Or maybe it's about like understanding fundamental principles and definitions or some kind of special intellectual abstraction process.
Interesting ideas, but a bit hard to pin down.
Exactly. And as our source points out, these explanations are pretty controversial. Like, what exactly is mathematical intuition? How can we be sure it's reliable?
Yeah, how do we know our intuition isn't leading us astray?
And so this is where nominalism might seem to have an early lead, right?
Because if you just get rid of those abstract objects, the problem goes away.
Yep. No mysterious objects, no need to explain how we know about them. But, and this is a big but, it's not like the epistemological problem completely vanishes for the nominalist.
Oh, why not?
Because they still have to explain why some people are good at math and others, well, not so much.
Yeah.
Like, if knowing math isn't about knowing these abstract objects, then what is it about?
If it's not about the objects themselves, what distinguishes a mathematician from, say, a historian or a poet?
Right. Some nominalists say that what we call mathematical knowledge is really just a special kind of logical or empirical knowledge. Like a mathematician is just someone who's really, really good at manipulating symbols and following rules within a formal system.
So it's all about the rules of the game, not about the objects themselves.
Exactly. But here's the thing for a philosopher. Does that really capture the richness of mathematical experience?
You mean like the feeling of discovery, the aha moments?
Yeah. When a mathematician proves a theorem, does it really feel like they're just shuffling symbols around? Or does it feel like they're uncovering some deep truth about the universe?
It's a really different way of thinking about what's going on in the mind of a mathematician.
For sure. Okay, problem number 2. The problem of application. How in the world is math, which seems to be all about these like ethereal, abstract things, so darn good at describing and predicting things in the real physical world?
Yeah, I mean, we're talking everything from launching rockets into space to designing bridges that don't collapse to predicting the weather.
And this is where that indispensability argument that we mentioned earlier comes in. This is the Platonists' big weapon.
Go on.
They argue that the very fact that our best scientific theories rely on math, and those theories make accurate predictions about the world, well, that gives us good reason to believe that the math itself is true.
Because if the theories depend on numbers and sets and those theories are right, then those numbers and sets must exist, right?
That's the line of reasoning. And if the math is true, then the objects it describes must be real. Big names in this argument are Quine, Putnam, and later, Collivan.
Okay, but doesn't that assume that the theories themselves are referring to actual mathematical objects? Like, couldn't you have a really successful theory that uses mathematical language without actually being committed to the existence of those objects?
That's a great question, and it gets to the heart of the debate. The Platonists would say, look, the theories work because they're accurately describing a mathematical reality. But our source points out that even if we grant that math is essential to science, even if it's indispensable, it's still a big jump to say, therefore, abstract mathematical objects must exist.
Right. There's still a question of how those abstract truths connect to the physical world. What's the mechanism?
Exactly. And there's also the issue of, what's it called? Underdetermination.
Underdetermination.
Yeah, the idea that you can often have multiple different mathematical structures that can all describe the same physical phenomena equally well.
Oh, I see. So, like, which one of those structures, if any, is the real one, the one that reflects the actual mathematical underpinnings of reality?
Exactly. It's a puzzle, for sure. Now, this whole problem of application is where nominalism faces a big challenge.
Because if you're denying that math objects exist, you have to come up with a different explanation for why math is so darn useful.
Right. And our source points out that several nominalist views, like Field's fictionalism, came about directly from trying to tackle this problem. They had to develop frameworks that could explain the power of math without having to say, well, it works because it's true about a realm of numbers.
That makes sense. So they're trying to explain the utility of math without buying into the whole package deal of Platonism.
Okay, problem number 3. The problem of uniform semantics. This one's a bit technical, but bear with me.
I'm all ears.
It's about whether we can have a consistent account of what mathematical statements mean and what makes them true or false.
Okay, that's getting into the nuts and bolts of language and meaning.
All right, it's about semantics. And the question is, can we treat math statements and, say, scientific statements about the physical world in the same way? Can we understand what makes them true or false on the same basis?
So, like, can we say that 2 plus 2 equals 4 is true in the same basic sense that we can say the sky is blue is true?
Exactly. Now, for the Platonists, this seems relatively straightforward.
How so?
Well, they can just say that math statements are true or false depending on whether they correctly describe those abstract objects, and scientific statements are true or false depending on whether they correctly describe the physical world. So they've got a unified picture.
They're all about correspondence with reality, just different kinds of reality.
Right. And even for mixed statements, ones that involve both math and physical terms.
Like the Earth's circumference is roughly 40,000 kilometers.
Exactly. The Platonists can still aim for a consistent account of meaning, especially if they're also, like, realists about science.
Right, if they think scientific theories are also aiming to describe reality.
But, as our source points out, getting this kind of unified semantics is a real headache for a lot of nominalists.
Because they're trying to avoid those mathematical objects.
Exactly. And so they often end up having to, like, reinterpret or rewrite math language in some pretty fundamental ways. And if you're changing the language that much, you might need a different kind of semantics to explain what makes those statements true or false.
Right. So you might end up with two different ways of understanding truth, one for math and one for science. That doesn't sound very unified.
Not at all. Okay, problem number 4 is the problem of taking mathematical discourse literally. This one gets to the heart of how we understand what mathematicians are actually saying.
Okay, explain.
So when a mathematician says something like, there are infinitely many prime numbers, should we take that as, like, a straightforward statement of fact?
Meaning?
Meaning, are they literally saying that there's this infinite collection of things called prime numbers out there in some mathematical realm?
I see. So it's about whether we can take their words at face value.
Exactly. And for the Platonist, the answer is usually a resounding yes.
Because for them, math statements are directly describing those abstract objects.
Right. So if a mathematician says something exists, the Platonist is happy to say, yep, it exists in that abstract realm.
Which makes sense from their point of view.
And a lot of people see this as a real advantage of Platonism. It allows us to understand math as it is without having to constantly translate or reinterpret what mathematicians are saying.
Yeah, no need to add extra layers of interpretation.
But, and this is a big one for nominalism,
right,
this literal interpretation is a huge problem for them, because their whole goal is to avoid saying that those objects exist.
So they can't just take those statements at face value.
Exactly. They have to come up with some other way of understanding what those statements mean.
I'm guessing this is where all those reinterpretations come in.
You got it. So, for example, modal structuralism, which we'll talk more about later, it brings in modal operators. Like, instead of just saying something exists, they might say, it is possible that there exists a structure such that...
Okay, so it's about possibility, not actuality.
Exactly. And fictionalism, which we'll also discuss later, it uses a similar trick. Instead of saying, there are infinitely many prime numbers, they might say, according to the fiction of arithmetic, there are infinitely many prime numbers.
So it's like they're putting math statements in quotation marks, almost.
In a way, yeah. They're acknowledging that math is a powerful tool, a useful way of talking about the world, but they're not willing to say that it's literally true in the way the Platonist does.
Interesting. It's like they're creating a kind of buffer zone between math language and reality.
Okay, on to the 5th and final problem, the ontological problem. And this one is, like, the granddaddy of them all.
Lay it on me.
It's the problem of, like, what exists?
Straightforward enough.
Right. It's asking, what is the nature of the entities that any philosophy of mathematics is ultimately committed to?
So we're not just talking about numbers anymore, but about what it means for anything to exist.
Exactly. And are we justified in believing that these entities actually exist?
Heavy stuff. So how does this play out for Platonism and nominalism?
Well, Platonism faces the challenge of having to really explain what these abstract objects are. Like, where are they? What are they made of? How do they interact with each other if they don't interact with the physical world?
Yeah, it's easy to say they exist, but much harder to explain what that existence actually amounts to.
And as our source mentions, nominalism isn't totally off the hook here either.
Really? How so?
Because even though they're trying to avoid those math objects, some forms of nominalism might end up being committed to other weird things.
Give me an example.
So like modal structuralism, which relies on this idea of possible worlds, well, some philosophers would say that if you really take the idea of possible worlds seriously, you're committing to a whole bunch of other abstract stuff.
Yeah, possible worlds are a whole other can of worms.
So the point is, the ontological problem isn't just about math objects. It's about carefully examining what any philosophy of math is ultimately saying exists and whether that view of existence makes sense.
It's about making sure your ontology is coherent and justified.
Exactly. So we've got these 5 big problems, right?
Right.
And as our source explains, there are like 3 main strategies that contemporary nominalists have come up with to try to solve them.
Okay, what are they?
The first 2, fictionalism and modal structuralism, they take what's often called the hard road.
The hard road.
Yeah, because they're trying to show that we can make sense of math without ever actually saying that math objects exist. Like, they're really trying to avoid making any commitments to those objects.
Sounds tricky.
Oh, it is. And then there's deflationary nominalism, which takes what's called the easy road.
Easier, huh?
Well, in a way, yeah, because they basically question whether talking about something in our theories, like, using numbers and sets in our equations, whether that really means we're committed to those things existing.
So they're going after the very idea of ontological commitment itself.
Exactly. Okay, let's start with one of the hard road approaches, which is Hartree-Field's mathematical fictionalism.
Right, fictionalism. Let's hear it.
The central idea here is that we can totally explain why math is so useful in science without having to believe that mathematical statements are actually true. In fact, Field goes even further and says that math, like taken literally, as making claims about these math objects. He says it's actually false.
Whoa, hold on. He's saying math is false. That's a bold claim.
Yeah, it's a head-turner for sure. But from his point of view, it makes sense. If numbers and sets and functions don't exist, then any statement that says they do must be false.
Okay, I can follow the logic there. But then what about statements like, all prime numbers greater than 2 are odd? Those seem true, even if you don't believe in prime numbers as objects.
Right. And Field acknowledges that. He says those kinds of statements, the universal ones, they're vacuously true.
Vacuously true.
Yeah, because there aren't any prime numbers to be counterexamples. It's like saying all unicorns are purple. It's true because there are no unicorns to disprove it.
Ah, okay, I see. It's true by default because the category is empty.
Exactly. But obviously, mathematicians talk about prime numbers all the time, and they don't usually add all these caveats about them being fictional. So to make sense of this, Field introduces something called a fictional operator.
A fictional operator?
Yeah, so instead of saying there are infinitely many prime numbers, you would say, according to the fiction of arithmetic, there are infinitely many prime numbers.
Ah, so you're framing it within a fictional context.
Right, which lets you talk about math in a way that's consistent with his view that those objects don't actually exist.
Clever move.
And Field's whole project rests on 2 really important philosophical moves. The first one is that he says the goal of math shouldn't be truth, at least not in the sense of describing a realm of objects. Instead, he says math should aim for conservativeness.
The conservativeness.
Yeah, it's a bit of a mouthful. It means that a mathematical theory is conservative with respect to a theory about the physical world if adding that math theory doesn't let you prove any new things about the world that you couldn't have proven without it.
So math is more like a tool for rearranging and clarifying what we already know about the physical world, but it doesn't actually tell us anything new about that world.
That's a good way to put it. He's not saying math is useless or arbitrary. He's saying that its power comes from its ability to make our reasoning more efficient, to shorten our derivations, but it doesn't introduce any fundamentally new information.
Okay, I'm following so far. But how does he actually show that math is conservative in this way?
That's where his second big move comes in. He has to provide what are called nominalistic premises, statements that describe the world without referring to any mathematical objects.
So he has to rebuild science from the ground up without using numbers or sets or any of that stuff.
Essentially, yes. He draws a lot of inspiration from Hilbert's work on the foundations of geometry, which showed how you could do geometry without relying on coordinates or measurement. Hilbert used concepts like point, betweenness, and congruence to build up a system that didn't need numbers.
Interesting. So he's trying to do something similar for, like, physics.
Exactly. Field tries to rework Newtonian gravitational theory without using things like real numbers or functions. He uses comparative predicates instead. Like, instead of talking about the mass of object X, he might talk about object X is heavier than object Y.
Okay, that's a very different way of talking about physics.
It is. And to link this back to standard mathematical physics, he relies on something called representation theorems. These theorems basically show that his nominalistic way of formulating things captures all the same possibilities as the standard mathematical way, even though it doesn't explicitly refer to those mathematical objects.
Sounds like a pretty ambitious project. But I have to ask, if Field is trying to avoid math objects, can he actually use all those sophisticated mathematical tools and theorems that he's relying on to make his case?
That's a great question, and it's one that philosophers have debated a lot. Like, can he use things like the completeness and compactness theorems of first-order logic if the proofs of those theorems themselves rely on set theory?
It sounds a bit circular, doesn't it? Like he's using the very math he's trying to eliminate to argue that you can eliminate it.
It does seem a bit tricky, right? And this is one of the main challenges to Field's approach. He needs a way to justify using those powerful mathematical tools without contradicting his whole philosophy.
Right. You can't just assume they're fine to use if his whole point is to show that we can do without them.
One way he tries to do this is by introducing the idea of a primitive modality, meaning he takes possibility and necessity as fundamental concepts that don't need to be defined in terms of possible worlds or other things. He tries to connect this primitive modality to standard model-theoretic consistency, hoping to find a way to talk about those metalogical theorems without relying on the full power of set theory.
So it's like he's trying to find a less ontologically loaded way to talk about the same concepts.
Exactly. But, as our source explains in detail, this strategy has faced a lot of scrutiny, and it's not clear that it fully succeeds.
It sounds like there are some pretty deep philosophical knots to untangle there.
For sure. And then there's the issue of Field's attempt to show that set theory itself is conservative.
Because set theory is kind of the foundation of a lot of modern math, right?
Exactly. And so even if he can show that other areas of math are conservative with respect to physics, if physics ultimately depends on set theory, then the problem isn't really solved.
I see. It's like trying to get rid of the foundation of a house without bringing the whole thing down.
And Field's nominalistic proof that set theory is conservative, well, it relies on the completeness of first-order logic, but the standard proof of that theorem often uses set theory itself. So we're back to that circularity problem.
Ugh, right back where we started.
And the source also points out that Field's approach is mainly focused on nominalizing scientific theories, not necessarily math itself, so it's limited in that way.
So even if it works for physics, it might not work for all of mathematics.
Okay, let's zoom out and assess Field's fictionalism. On the plus side, that traditional problem of how we know about math objects kind of disappears.
Because he's saying they don't exist.
Yep, no objects, no mystery.
But I bet that creates other problems.
It does. It raises a new question. What exactly makes someone a mathematician? If they're not gaining knowledge of these abstract objects, what are they doing?
It pushes the question of mathematical knowledge in a different direction.
Right. Field suggests it's about logical knowledge, but then you have to have a really strong account of what logic is and how we know about it. And when it comes to application, well, Field does offer an explanation for why math is useful without assuming it's true, but it's not clear that his approach reflects how scientists actually use math in the real world.
Yeah, it seems like more of a theoretical reconstruction than a description of actual scientific practice.
Right. And there are debates about whether it can be extended to all areas of science, like, for instance, quantum mechanics, which is notoriously weird and hard to fit into neat philosophical boxes.
Quantum mechanics always seems to throw a wrench into the works.
It really does. And there's also the point that scientists need to, actually believe their theories to some extent, even if they're nominalistic theories. So what does that mean for the fictionalist? Can they really say, believe this theory, but don't believe the math it's based on?
That's a tricky line to walk.
It is. As for semantics, well, fictionalism kind of has one foot in both camps. On the one hand, it tries to treat math and science similarly in the sense that it's concerned with what makes those statements true or false. But on the other hand, that fictional operator introduces a whole different layer of meaning for math statements.
Right. It's not just about whether they correspond to reality anymore.
And of course, fictionalism,